All right, so this is our plan for this week. We're going to cover 9.4 and 9.5. 9.4 is parametric equations, and 9.5 is polar coordinates. So these two things are both brand new to everybody. It's going to be like a crucial week to make sure that you're staying with us. And then next week we're going to do a quiz on 9.4, 9.5. That will actually be your third quiz. And then we'll go one more section, which is 10. Well, actually, we might do two more sections, 9.6, 10.1. And then I'm thinking that we'll be asked to test on that following week. We haven't been given our testing schedule just yet as to which subjects are testing during which weeks, but I'm thinking ours will be then, and then that will be your second test. So we're going to do the notes together on 9.4 today, and then your homework's going to be the 9.4 homework due Wednesday, and then 9.5 on Wednesday, and 9.5 homework due on Friday, and then we'll go over the warm-up for 9.5 on Wednesday. Our plan for the week. So 9.4 is called parametric equations, okay? A parametric equation are a set of equations, so it's actually a systems of equation that express a set of quantities as an explicit function of number of independent variables known as parameters. So they call the variables parameters this time. And these equations will introduce the third variable, which is t. So you're going to get x, you're going to get y, just like you normally get in an equation, but now you're going to get something called t, which is time. So parametric has a shape just like all the other equations that we would have if we were to graph it, but for time it actually has like an elapsed time, so it has a direction on it. So it's a little bit different in the graphing because it has a direction and it has a third variable, which is t, but they're just systems of equations. You're going to get two equations with three variables, and then we're going to talk about how to plot them. So this is what a parametric could look like on the left. The difference between a parametric and a rectangular. These are simply just like a parabola, but on the right hand side it has, okay, on the right hand side is your typical parabola. On the left hand side is your parametric graph. Oh wait, F rose. Okay, so right hand side is your typical parabola. This is a y equals x plus 3 squared plus 1. So it's shifted left 3, up 1. And it's pointed up, and then on the left hand side you have your parametric. So really the difference is not in the shape. The shape is the same, but the difference is that each of these have little arrows, and the directions telling you where it was when time was, let's say, 0. So at the beginning it was over here, and where it was at the end when, I don't even know, time was like 4, something like that. So it starts at where it would be the lower time, and then the arrows progress in the direction of where the higher time would be. So the plane curves are continuous. They're not going to stop and start. So the graph can be traced with a finger without lifting your pencil from the paper or your stylus from your iPad. And the points are plotted in the order of increasing values of t. Arrows indicate the direction or orientation of the curve. So again, it's going to start at one point, and as you move from left to right, you get the arrows moving in that direction. So just like our basic functions of graphing, we're going to take these equations and we're actually going to just make a t-chart. So if they're continuous and on the interval of I, then the set of ordered pairs f of t and g of t, which is kind of be like your x when you plug in the t, your y when you plug in the t, will just make that curve. So there's going to be two separate equations, an x equals and a y equals, like this and this. You're going to take values for t and plug them into the variable, and then you're going to set up two different points, which I'll show you in a second. And again, t is called the parameter, so it's a variable, but in this, it's specifically called a parameter. All right, so this is what your t-chart will look like. It's actually got an extra column because we're going to do one column for t, we're going to do one column for x, we're going to do one column for y. So if I have x equals something with a t and y equals something with a t, I'm going to take whatever t is. So let's say I think t is 0. I'm going to plug it in here. I'm going to plug it in here. My x value is here. My y value is here. Then I'm going to take t is 1. I'm going to plug it in. I get my x value. Plug it in, get the y value. Maybe t is 2. Plug it in and get the x and the y. And then I graph only the x, y coordinates. So t itself does not actually go on my graph. Anybody still copying that down? Okay. So here's an example. Sketch the curve given by the parametric equations x equals t squared minus 4 and y equals t over 2. Man, I'm so tired this morning. Sorry, I keep yawning. I am not sleeping good during this crap. All right. So let's start with the x, right? So the t values are what we're going to plug in. And this time it actually gives you a set of numbers to plug in. It's saying t is from -2 to +3, including -2 and +3. So I'm going to plug in -2, -1, 0, 1, 2, and 3. I'm going to plug in the numbers that they tell me to do. If they don't give it to you, then you can kind of just plug in a set of numbers like we're used to, like a -1, 0, and +1, that kind of thing. But if it gives you the set, you want to plug those in. So I'm going to take and plug them into the x. So x would equal t squared, which is -2 squared minus 4. That's 4 minus 4, which is 0. Then I'm going to plug in -1 squared minus 4, 1 minus 4, which is -3. Then I'm going to plug in 0 squared minus 4, 0 minus 4, which is -4. Then I'm going to plug in 1 squared minus 4, 1 minus 4, which is -3. Then I'm going to plug in 2, 4 minus 4, which is 0. And then I'm going to plug in 3. And that's 5. And then I'm going to repeat that whole process with the y. So I'm going to take the y, which equals 1/2 t, or t over 2. And I'm going to plug in first -2, -1. Then I'm going to plug in -1, and it's -1/2. Then I'm going to plug in 0, and it's 0. Then I'm going to plug in 1, and it's 1/2. Then I'm going to plug in 2, and it's 1. And then I'm going to plug in 3, and it's 3.5 or 1.5. Or 3/2, sorry, or 1/2. So this is 0, 1/2, 1, and 1.5. So I'm just taking the t and plugging it into the x equation, and then taking the t and plugging it into the y equation. So then my coordinate points are the x's and the y's. So 0, -1, -3, -1/2, -4, 0, -3, 1/2, 0, 1, and 5, and 1.5. And then I'm going to take and plot those points. So 0, -1, -3, -1/2, -4, 0, 0, 1, -3, oh wait, hang on, -4, 0, -3.5. This is wrong. 0. Eek. 0, -1, 2 there. Okay. 0, 1, and then 5 and 1.5. 1, 2, 3, 4, 5, 1.5. So this is a curve. It's almost like a parabola that's turned on its side. And so I connect it like this, right, to make my curve. But because it's a parametric equation, I need arrows. I need the arrows pointing away from the smallest t and towards the largest t. So since we went this way, we started with this point here. This was our first point, and we worked our way in that direction. That's the direction of our arrows. There's no amount of arrows that you need, like a specific amount of arrows that you need, but you just need them pointing away from the first point you got from plugging in the smallest t and plugging it towards the last point you got by plugging in the largest t. Questions on that one? So sometimes they're going to be lines, sometimes they're going to be curves. You just want to plot your points. it's, oh, t over 2. So I'm going to type. Okay, so we can use a graphing calculator to graph these, but we actually change our mode. So we're going to learn how to put our calculators into something called parametric. So eventually we're going to get into parametric and polar, but for today we're just going to do the parametric one. So if you have your graphing calculator with you, you can take it out and open it up. So here's mine. So the first thing we're going to do is actually do the change of the mode. So if you go to mode on your calculator, normally we're flipping back and forth between radian and degree, okay? But on the bottom, or not on the bottom, but a little ways down, fifth line, you see it says function, parametric, polar, and sequence. So if you scroll over to parametric and you hit enter, you just switched your calculator into parametric mode. We're going to do polar next, and that's the next thing that's there. You don't have to put the arrows in. Valentina, you mean on the graph? It didn't have to be on the specific points. Is that what you mean? For the arrows? I knew you. Yeah, okay, no, you don't. It can be anywhere on the curve. So the arrow, the location of the arrows in your graph doesn't matter. Okay, so if this was our, I put it in parametric, now I can quit out of here. Now, when I go, let's say I want to go to graph this. If I hit y equals, notice that you're given two equations now. You're given an x1 for t and a y1 for t, and the variable automatically changes to t. So let's say I go back, which actually is this the one that we were just on? Say I go back to the example that I just had, and it's t squared minus 1. Then okay, so t squared minus 1 is already there, right? But that was first, so let's do that. T squared, when I hit the variable button, I get the t. So it changes it, and already knows it's not x anymore. T squared minus 1, and then t divided by 2. Hit enter on those, hit graph on those, and there's my graph. Now, it is not the exact window that we had, which we can adjust because we know the window. So if I go to window, and I want to make, these are now t's, right? So if I wanted to make it match my graph exactly, we went from -3, nope, we went from -2 to +3. And now it should match your graph exactly. It's not going to have the arrows. This is one of those times that you are smarter than your calculator, because it's not going to have the arrows to know what direction it went in, but it will have the shape of the curve. So you can use a graphing calculator to check these graphs. Questions on that? Jacob, make sure I can see your face, please. Jacob, make sure I can see your face, please. Thank you. We're doing notes for 9-4. All right, so this one says sketch the curve given by the parametric equations x equals t, or 4t squared minus 4, and y equals t, given that it's -1 to 3/2. So I'm going to start with the smallest t being -1. I'm going to jump in increments of whole numbers. So I'm going to go to 0, I'm going to go to 1, and then 3/2 is 1.5. So this is plenty of points. 4 is plenty. I don't have to do the halves in between, okay? Just make sure you cover the ones that they give you if it says or equal to, which is what's happening here. So now I want to plug these in. So I'm going to plug in for x. X would equal 4 times -1 squared minus 4, which is 4 minus 4, or 0. X would equal 4 times 0 squared minus 4, 0 minus 4, which is -4. x would equal 4 times 1 squared minus 4, 4 minus 4, which is 0. And x would equal 4, 1 1/2 or 3/2 squared minus 4 is 4 times 9/4 minus 4. The 4's get canceled. 9 minus 4 is 5. So those are the values for x. Then for y, it is what we plug in. Y equals t. So this would be -1, 0, 1, and 1 1/2. So when we make these coordinate points, there's 0, -1, -4, 0, 0, 1, and 5, and 1 1/2. And then I'm going to graph them. So 0, -1, -4, 0, 0, 1, and 5, 1, 2, 3, 4, 5, 1 1/2. And it goes in the direction from smallest t to largest t. So my arrows, again, point this way. And then I'm going to check it in my calculator again. So I plugged in my equations. X equals 4t minus 4. Y equals t. I hit graph. And again, it doesn't match exactly because I need to set up my my window. So I'm going to do window from -1 to 3/2. Then I'm going to graph it. And it matches my curve. Again, the arrows aren't there, but it will match your curve. Isn't 0 squared? No, 0 squared is 0. So again, you can use a graphing calculator to check these. I obviously haven't made your quiz or your test on this, but if it's a quiz or test in which you're going to do something like that where you're going to graph it, you'll give me your t-chart. So you'll have a t-chart and you'll have to give me the t-chart filled out. So obviously you can use the graphing calculator to check it, but you would need, if I let you use a graphing calculator, you would need the, you would have to have the work for the t-chart. So make sure when you're doing the homework, you're practicing that skill. Questions so far? Okay. Now we get into eliminating the parameters. So there's 3 different kinds of problems within this section. The first is that, graphing using the t-chart, and this is the second one, eliminating the parameter. So we're actually going to take these 2 equations that have t in them and get rid of t, which will make it like one equation that we can graph because it will be a shape that we're normally used to, like a parabola or a line or something like that. Now, these are not exact representations of these. These are approximations of what the parametric function would be. So this says many curves are represented by the sets of parametric equations have graphs that can also be represented by rectangular equations, just like the ones we just did sort of look like a parabola. So we could have taken an equation for a parabola and graphed it, and it would have been pretty similar. So to do this, we're going to take, there's going to be, again, 2 equations. We're going to solve one of the equations for t. So we're basically using substitution. Solving one of the equations for t and then plugging that into the second equation to eliminate the t, making it one xy equation. And then you'll graph it using what you know about parabolas or lines or square roots or anything like that. The domain of the functions need to be restricted. So when you get, remember, domain restrictions, we look for things like a variable in the denominator, or a variable underneath the square root, or the combination of these, a variable in the denominator underneath the square root. So if it's in the denominator, we would say that variable cannot equal 0, or the denominator cannot equal 0. And if it's underneath the square root, we say it has to be greater than 0. If it's a variable in the denominator underneath the square root, then we say it has to be greater than 0. So it may ask you for domain, and that's what those 3 cases are what's going to happen. If it's not one of those 3, if it's just a line or anything like that, then there's no domain restriction. But you got to remember to check for the domain restriction. And like it says, it may need to be restricted to graph it accurately. So you might have a restriction on your graph. Anybody still copying that down? So for like, okay, so it says graph by eliminating the parameter. We have two equations with three variables, right? And the goal here is to get rid of t. So I want to look at one of these equations and say, what's the easiest one to solve for t? If I wanted to solve for t for the x one, I'd have to add the 4 and then square root it. If I want to solve for t on the y, all I have to do is multiply by 2 on both sides. So I'd get 2y equals t. So step 1 is figure out which one you want to solve for t. Okay, then I'm going to take that and I'm going to plug it into the second equation in place of the t. So I get x equals 2y squared minus 4. And I get x equals 4y squared minus 4. So this is a parabola, okay? The 4, you can do these different ways. You can either go back to your transformations. We know if it's a y squared, it's turned to the right or to the left. Or we could put it into standard form like we just did, where this, the 4 goes on the side with the x, so this would be x plus 4 equals 4y squared. And then I have to get rid of this 4. So it would be like 1/4 x plus 4, or equals y squared. Or you could switch that order around, and I'd get y squared equals 1/4 x plus 4. So this tells me it's a y squared, which means it's turned right or left. It's a positive 4p, which means it's going to be pointing to the right. And I would just go left 4 for the x. 1, 2, 3, 4. Positive. I don't have to be exact. Okay, this is an approximation. So it's not asking to draw the directrix or anything like that. All you would need for that is what direction this is going. And then again, you can always use your graphing calculator to check it by plotting the original or the new one, okay? The new one that for y squared, a lot of our calculators don't do the y squareds. So you would go back to the beginning, which is just t squared minus 4, and then 1/2 t. And then you'd hit graph, and don't restrict your domain. So make your window like -10 to +10 like it normally is. And there's what my graph looks like, which matches what I got. Again, I plugged in the original equations, and then I adjusted the window -10 to 10, and then I graphed it. Now there's no arrows along the curve this time because we don't know where it would have been for t to be 0 and t to be 3 or anything like that. This is an approximation of the graph when you eliminate the parameter. So eliminating the parameter, you are approximating your graph, and you won't have the arrows like you do on your normal parametric functions. Questions on that one? Got attacked by mosquitoes this morning. Okay, example 4, same set of instructions, graph by eliminating the parameter. So we need to get rid of one of these equations, or we need to solve one of these equations for t. This time they're both a little complicated. If I want to get rid of this down here, I'd have to square both sides of the equation. I'd get x squared equals 1 over t plus 1. And then I'd have to solve for t. So I'd have to multiply here, here, and then divide both sides by x squared. And then subtract 1. Which is a little complicated, but the right hand side is not much better because there's 2 t's. If I multiply by t plus 1, I'd have to get everything to the same side, so I'd have to distribute this. get the t's to the same side, take out the t, and then divide. So t would equal y over 1 minus y. So in this case, they're actually both pretty complicated. I would say just pick, and I would say once I solve the first one, I would take this and I would plug it into this equation. So that's going to look like this. T, or y equals, wherever there's a t, I'm doing 1 over x squared minus 1. So then this would be 1 over x squared minus 1 plus 1. These are going to cancel, and I get y equals 1 over, 1 over x squared minus 1 all over 1 over x squared. I'd want to get this into one fraction. So this becomes 1 over x squared minus x squared over x squared, or 1 minus x squared over x squared, all over 1 over x squared. Then keep, change, flip, and I get 1 minus x squared. So y equals 1 minus x squared. If I put this in standard form, so if I want to talk about transformations, I can just do y equals negative x squared plus 1. And I know that that's a parabola pointing down with my shift up 1. So it'd be here, arrow down. If I want to put it into standard form that we just worked with, then the x squared would go on the side by itself. So this would come over here. The y would come over here, and I'd get negative y plus 1. I'd know it's a parabola that points down. My vertex is at 0, 1. And the p would be 1/4. But again, you just need the direction for it. So that's about as complicated as they get on that stuff. Obviously, that's a lot of like review of algebra skills. Sometimes the equations do get kind of crazy. So just work with it as best you can. But again, your goal is to eliminate the t and then graph it. And it should be a graph that you can graph, either a line or a parabola or something like that. Now, if it asks for domain on these, and that's where that domain reminder came from, you would have to come back up here and say t plus 1 would have to be greater than 0, so t would have to be greater than negative 1. And here, t plus 1 cannot equal 0, so t cannot equal negative 1, which is fine on that domain. T would have to be greater than negative 1. Why is it 1 minus x squared? Well, I mean, that's all of this work here. So I started by plugging, I solved here, solved t, 1 over x squared minus 1, and then I plugged that into the top and to the bottom. And then I simplified the denominator by canceling out the negative 1 and the positive 1. And that's this step. And then I gave the numerator a like denominator, so I had to change 1 to be something over x squared, which is x squared over x squared. And I get this, which is 1 minus x squared over x squared. Take the bottom, bring it to the top, but flip it. The x squared canceled. And then I got just 1 minus x squared. So y equals 1 minus x squared, and then I just moved it around and put it in standard form. Okay, so on this one I graphed it, right? Now my window is still negative 10 to positive 10, but look at my graph. What happened to the left side of my graph? Anybody know why this is happening? There's a domain restriction, right? So because of the square root function here, like this square root function tells me that t plus 1 would have to be greater than 0, right? So t plus 1 would have to be greater than 0, which means t would have to be greater than negative 1. And then for this one, t plus 1 cannot equal 0. T cannot equal negative 1. Well, this already has that in it, so I'm not worried about the second one. The first one takes care of it. But that is why I lost the left side of my graph. So when we're doing the approximations, they can literally be approximations. I don't need you to stress too much about the domain restriction. But if you do see a domain restriction, know that that's why it's happening. Third part is finding the parametric equation. So what happens if I give you two equations? One's going to have a t in it, one's not. And your result needs to be a systems of equation that both have t. So you need an x equals and a y equals. Both of them should have some sort of t in them. So you'd have to figure out, obviously, what that is. So you're going to be given the equations with the eliminated variable. Like, let's just say it says x equals y, and there's no t there. And then y equals x plus t, or something like that, right? So you have to substitute the equation with t into the initial equation, and the solution is going to end up being 1 x equals with a t in it and 1 y equals with a t in it. This is how you know you've got your actual system that is a parametric equation. So you're going to start with two equations, but one of them is not going to have the t. You have to solve the second equation for the t and plug it in to the first equation, resulting in two equations that have t. So they look like this. Okay, this is actually two questions, so try to ignore B while we work on A, because I know that's a little confusing. It says find a set of parametric equations to represent the graph of y equals 1 minus x squared using the parameters t equals x. So I'm really just looking at these two equations for the first one. Y equals 1 minus x squared and t equals x. I need two equations that both have both have t in them. I already have x equals t. There's the first one. But my y equals equation does not have a t in it. So I have to look to the second equation, which is this first one in the case, the one that already has x in it. And in place of the x, I have to plug in what it equals, which in this case is t. And I get y equals 1 minus t squared. And that's it. That's all you have to do. Make it so that you have two equations. One's a y equals, one's an x equals. They both now have to have t in them. So if I wanted to graph this, then you could graph it, and I could give you parameters, and you could do your t-chart like we did at the beginning. All right, second equation, same initial equation. So we're saying y equals 1 minus x squared, and t equals 1 minus x. I need two equations at the end. One x equals, one y equals, and they both have to have a t in them. So go back to the ones that they give you, identify which one has a t in it, which again, this time is the x. And I'm going to solve it for x. So if t equals 1 minus x, then I can subtract the 1. And then I can multiply or divide anything by negative 1. So negative t plus 1 equals x, or x equals negative t plus 1. That's the first equation. And you could switch that order. It could be 1 minus x, 1 minus t. That's fine. Then I have to take that, whatever x equals, so we're using substitution, and plug it in to the x of the second equation. So I get y equals 1 minus negative t plus 1 squared. So I need to expand and FOIL that out. So I could do first, so 1 minus negative t times negative t is t squared. Negative t times 1 is minus t. 1 times negative t is minus t. 1 times 1 is 1. 1 minus t squared minus 2t plus 1. And I get 1 minus t squared plus 2t minus 1. These cancel, and y equals negative t squared plus 2t. Or you can reverse the order on that, doesn't matter. So negative t squared plus 2t. And again, these can each be written with the reverse order, making t positive. So I could have said x equals 1 minus t, and y equals 2t minus t squared. Either of those are right. The order there is not important as long as the signs are on the right terms. Questions on that one? So again, in this section, there's 3 different types of questions. The first is graphing using a t-chart, where you're plugging in the value for t and you're getting xy. The second one is where you're eliminating the parameter, so you're solving one of the equations for t, plugging in and getting rid of it. And the third one is this, where you're creating your system given one equation that has t and one equation that doesn't.